and welcome to another video on my channel. Today we will be talking about another limits problem or another method of solving limits called the squeeze theorem. So without further ado, let's move on to the actual main content of this video. Now, what exactly is the squeeze theorem? The squeeze theorem is a tool for finding limits when the function is bounded between two simpler functions. So, let's say we have a function f of x and we have a function g of x. Now we know we have a function h of x where h of x is less than f of x, but it's greater than g of x. So what we can say is if limit f of x and g of x is equal to each other or a certain value, we can call that y, then the limit of the middle function h of x is equal to L. And that's basically what this statement over here says, except for the fact that they did g of x and h of x on the outside and f of x on the middle. So, and then over here it's the key insight. This is basically just the word form. This is just the word form of the mathematical statement. So, let's move on to why should we even use this. This is when to apply the squeeze theorem, but also why to apply the squeeze theorem. Now, the first is oscillating functions. Those limits can be tricky to calculate, especially when they're approaching infinity, so that's why you would use it. Now, if you have 0 by 0 and factoring is a little more difficult, you can also use this. Complex functions, basically, if it's even more complicated and even factoring won't work, which just kind of ties into the second method, which was indeterminate forms, or the second reason. Then number 4 is rapid oscillations, not just oscillating functions, but functions that oscillate very rapidly, and it's difficult to tell the limits using regular methods. So let's move on to the example, or should I say examples. Example 1 is an oscillating function, a pretty simple oscillating function which oscillates quite rapidly between -1 and 1. The problem is we have to find limits as x approaches 0 of x squared sine of 1 over x. Now, as you can see, this very challenge thing over here will actually be the solution. So, if we start by inserting a new card, and then if we start actually by saying, okay, if you're saying it's bounded by -1 and 1, you can say -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. This can be turned into something else, which we'll get onto in a few moments. But this is just using what we're given and putting it in an inequality. So then what we can do to get that function x squared sine of 1 over x is we can multiply both sides by x squared. So if we open this back up and multiply both sides, or all the parts of the inequality, by x squared, we get negative x squared is less than x squared sine of 1 over x is less than x squared. As you can see, this is all completely true, and we're just using basic algebra. But here's where the real magic comes in. If we take the limit of the two sides as it approaches to 0, that means the limit as x approaches 0 of negative x squared is actually equal to the limit as x approaches 0 of x squared, and both of these limits are equal to 0. Following this theorem, if we have both of the limits equal to 0, according to the squeeze theorem, the limit as x approaches 0 of x squared sine of 1 over x should also equal to 0 by the squeeze theorem. So our final answer is limit as x approaches 0 of x squared sine of 1 over x is equal to 0, same as the two other functions that we figured out would bound this. So that's about it for this problem. Now let's move on to the solution. Now the solution, as I said, if you ever want to skip through there, is basically if you're just using these videos for practice, or you were faster than me and you solved it before me, then you can go in and check your answer there quickly so it doesn't end up wasting too much of your time. But I would always recommend you to stop and wait, as you might learn something and you might have done something wrong and you might have not figured out how. So this is all showing all the steps while also me explaining it to you versus just a text saying what the steps are. Here you go. Here's the solution. The answer is equal to 0. First, we have to establish the bounds. Then we have to multiply by x squared, evaluate the limits, and apply the squeeze theorem. Same standard steps, and you're actually going to see these 4 standard steps. Steps 1 and 2 could be the same step, one step, multiple steps, but you would evaluate the limits of the bounds and apply squeeze theorem for sure. Our second example is a limit at infinity, where we would have limits as x approaches infinity of sine x over x. Now, what happens over here is, instead of going to 0, where there is an identity for this, we're going to infinity for this. And if we go to infinity, the problem is that sine would continue oscillating while x grows infinitely, so we would not exactly be sure how this would work. So our key question is, how does oscillation behave when divided by large x? Basically, how would a function oscillate if we have divided over 1,000,000 or 1,000,000,000 or 1,000,000,000 or even infinity for that matter? So that's what we're going to figure out in this problem. So the first step we have to do is figure out 2 functions that this should oscillate by. Now, the 2 functions that we are going to use is -1 and 1, just like we did for the last one. And we're going to use just the base sine of x function to do this. Now, the reason we're going to be using the base sine of x function is bounding sine x over x is difficult, as we don't know the behavior of it. But sine x, we do know the behavior of it. It's a very simple function, so we're going to bound it by -1 and 1. Now, as you see over here, we have -1 is less than or equal to sine x is less than or equal to 1. Now, the next step in this problem would be to divide by x, because we want to get the function in the middle so we can evaluate the 2 limits. So now that we have the first 2 steps done, we can evaluate the 2 limits. As x approaches infinity, -1 over x goes to -1 over infinity, and 1 over infinity is 0, and -0 is just 0. Same thing goes for 1 over x. The limits as x approaches infinity, this time not 0, of -1 over x is equal to the limit as x approaches infinity of just plain old 1 over x. But this limit is equal to 0 also, so we can't just say that they're equal but not provide an actual value. So limit as x approaches infinity 1 over x is equal to 0. Now, since these 2 limits are equal to each other, that means that the limit of sine x over x is going to be equal to 0 as well. So our final solution is limit as x approaches infinity of sine x divided by x is equal to 0, just like the two functions we defined that bounded it. So that's our final answer. Now let's move on to the solution slide. And here's the solution to example 2. Same thing, we're going to use bounds for the sign, divide by 1 by x, evaluate the limit, and apply Squeeze's theorem. Or not Squeeze's theorem. As far as I know, there's no one actually named Squeeze. So it's just going to be apply Squeeze theorem. By the way, if you didn't know, the Squeeze theorem was also called the sandwich theorem. The example 3 is product of functions. Now, let's say we have two functions multiplied by each other. So what's going to happen here is instead of having functions that divide by each other, we're going to have functions that multiply. Now, this is actually still quite simple, so it's not really much to worry about, but it's a good thing to know just in case, because sometimes the values can be a little different, and that way Squeeze's theorem will not exactly work. So, our problem is to find the limit as x approaches 0 of x cosine 1 over x. So the first step is to do bounds. The bounds we're going to do is cosine 1 over x. Now cosine 1 over x has the same bounds as sine 1 over x, which is negative 1 and 1. So we have negative 1 of cosine 1 over x is less than 1. And these are our initial bounds. Now what we have to do is multiply it by x. So what we're going to have is negative x times x cosine 1 by x is less than or equal to x. Now what this does is this makes sure we have our original function in the middle. Our third step would be to divide by to evaluate the limits. So if we have as approaches to 0, the limit as x approaches 0 of negative x is equal to 0, which is also equal to the limit as x approaches 0 of x itself. So here you go. Here is the limit as x approaches 0 of negative x and as x approaches 0 of regular x. So since these two are the same, that means our original problem, limit as x approaches 0 of x cosine of x, is also equal to 0. Now keep in mind, this function was actually extremely similar to our first problem, except this is cosine and the other one was sine. And here you go, the solution to our third example. Here is the solution slide where it's saying establish the bounds, multiply by x, and evaluate the limits, and apply Squeeze's theorem. That's pretty much about it. That's all we have for our examples. So thank you for listening to these examples, but we still have a few more slides left. This is basically the approach that you should pretty much always do. Like, this is the method to solve problems using Squeeze's theorem. First, we need to identify the bounded functions and bound them. Now, a key thing would be to look for trigonometric functions, as those are very easily bounded. The second step is to use multiplication and division. Now, multiplication and division can create useful bounds, basically having the function in the middle. Then, another one is to choose simple bounding functions with easy calculable limits instead of making something very complicated and then having to multiply by something very complicated, and then you'll get a complicated limit, and Squeeze theorem just becomes 10 times more complicated that way. That's a lot of complicated. So, the final thing is to verify both bounds and to make sure they approach the same limit, as this shows that Squeeze's theorem will actually work. So, these are the advantages and the applications. Now, This is the best method pretty much to use if we want to handle oscillating functions effectively. It's simpler than advanced techniques that involve differentiation, like L'Hopital's rule. Then, this also provides a pretty systematic and logical approach. This builds mathematical intuition, basically helping you understand the key concepts behind all of the problems and examples and the theorems. And this is actually one of the main things that will be used to prove trigonometric function derivatives. Thank you very much for watching. See you in the next one. But before that, please make sure to like, subscribe, and hit that notification for more awesome videos just like this. And please comment down below what you like more, which topics you like, which topics do you want to see me covering, because this really helps the channel. This will help you also, as you'll learn more, and it will help me to become a better creator for all of you guys. So, thank you so much, and see you in the next one. Bye-bye.